So what is really at the heart of a black hole? For decades, physics has given us this one kind of weird answer, a singularity, a point of infinite density where reality just breaks. But what if that's completely wrong? What if, at the very center of these cosmic monsters, there's something solid, something almost like a crystal? Let's dive into this wild new idea.
All right, so really wrap our heads around this new theory, we first have to talk about the huge problem at the center of the old one. See, the standard model of a black hole, well, it leads us to a place where our understanding of the entire universe just completely falls apart. I mean, this is the question, right? It's the one that has tied physicists in knots for pretty much a century. We have this fantastically successful theory of gravity, Einstein's general relativity, but when you point it at the core of a black hole, it spits out an answer that makes most physicists, frankly, deeply uncomfortable. And here it is. This is the problem. General relativity predicts a singularity, a single point where the mass of an entire star gets crushed into literally zero volume, creating infinite density. Now you should know, whenever the word infinity pops up in a physics equation, it is a huge red flag. It's basically the universe's way of screaming at us, nope, your theory is broken right here. You're missing a piece of the puzzle. So, what could that missing piece actually be? Well, let's explore a fascinating new theory that avoids this whole infinity problem altogether. It suggests that deep inside a black hole, physics doesn't break down. It just changes state. And here is the absolute key difference. Instead of matter just collapsing forever and ever towards an infinitely small point, this new theory says the collapse stops. It actually hits a fundamental limit, a maximum possible density. And at that exact point, the very nature of reality itself changes. To get how this happens, we need to completely rethink what the vacuum of space is. This theory proposes that it's not some empty void, but a real physical substance made of these fundamental grains. The best way to think about it is like water. If you put liquid water under enough pressure at the right temperature, it freezes solid into ice. The theory says the vacuum of space can do the exact same thing when you squeeze it to its absolute limit. So just picture this. A massive star collapses. The pressure becomes so immense that it starts squeezing the very grains of the vacuum itself. Now there's a fundamental limit to how tightly you can pack things. It's called the Kepler conjecture, and it's about 74% of the available volume. Once the pressure inside the black hole forces these grains to hit that maximum density, the collapse simply halts. The liquid-like vacuum freezes solid, and it forms a perfectly ordered crystal core. No singularity, just a bizarre new state of matter. Okay, a crystal core is a seriously cool idea, but I know what you're thinking. It sounds like pure science fiction. How could we possibly test what's inside an object we can't even see? Well, it turns out we might be able to listen to it. Of course it should. I mean, a solid surface has to behave differently than an empty void, right? If something were to hit that surface, you'd expect it to create an echo. And in the bizarre world of black holes, the sound we're listening for isn't sound at all. It's a ripple in space-time itself, a gravitational wave. That theory actually predicts a very specific way these echoes would work. So when two black holes merge, they unleash this incredible burst of gravitational waves. In the standard model, those waves just fly out into space and that's it. But if there's a crystal core, some of that wave energy should smack into that hard surface, reflect off it like sound bouncing off a canyon wall, and then radiate out as a series of faint, repeating echoes. And here is where it gets truly amazing. The theory makes a prediction that is just stunningly precise. For a black hole that's about the mass of our sun, the time delay between the main gravitational wave and its very first echo should be almost exactly 20 microseconds. So this isn't some vague idea, it's a hard number we can actually go out and look for. So have we found these echoes? Well, the short answer is not yet. Detectors like LIGO are actively hunting for them right now, but the signals are probably just too faint to be picked out from all the background noise. But this is where science gets really exciting. There's an upcoming upgrade, it's called O5, that should be sensitive enough to finally find them. And that means this theory faces a clear test. If O5 detects, say, 100 black hole mergers and finds 0 echoes, this beautiful crystal core idea could be definitively ruled out. But here's what's so powerful about this idea. It goes way beyond just getting rid of the singularity problem. This single concept, a crystal core, also starts to elegantly solve other major, nagging paradoxes in black hole physics. Take Hawking radiation, for example, the famous idea that black holes can slowly evaporate. The standard explanation involves all this super complex quantum field theory and virtual particles popping into existence right at the event horizon. But the crystal core theory offers a much more mechanical, almost intuitive explanation. The black hole radiates heat simply because its hot, vibrating crystal core is cooling down, sending out phonons, basically sound waves, into the vacuum.
And here's the kicker. When you actually do the math and calculate the temperature of the black hole based on these simple mechanical vibrations, you get the exact same answer that Stephen Hawking got using a completely different and way more complex method. I mean, that's an incredible result. When two totally different models lead you to the same precise answer, physicists really start to pay attention.
It also provides this just beautiful solution to the famous information paradox. So the paradox asks, what happens to the information of all the stuff that falls into a black hole? Is it just destroyed forever? Because that would violate a fundamental law of quantum mechanics. This theory says, no, of course not. The information gets encoded as tiny little defects on the 2D surface of the crystal, and as the black hole evaporates, that information is released in the pattern of the escaping phonons. Nothing is ever lost.
And that brings us to the final and maybe the most profound implication of this whole theory. What is left behind when a black hole finally finishes evaporating completely?
See, in this model, the evaporation doesn't go on forever until the black hole just vanishes into nothing. It stops. It stops when the crystal core shrinks down to its smallest possible size, a single, stable grain of the vacuum. This final little object is called a Planck remnant. Now just think for a second about the properties of these things. If this theory is right, the universe should be absolutely filled with these Planck remnants. They're the leftovers from primordial black holes that formed in the very early universe and have been slowly evaporating ever since. They would be incredibly old, perfectly stable, electrically neutral, and they wouldn't really interact with much of anything. And this leads us to our final, pretty provocative thought. An ancient, stable, non-interactive substance spread throughout the entire cosmos, making up a huge amount of its mass. Does that sound familiar? The properties of these Planck remnants are a perfect match for the description of dark matter, the mysterious, invisible stuff that makes up 85% of the matter in our universe. Could it be that the answer to one of the greatest mysteries in cosmology has been hiding inside another one all along?